Howdy everyone, welcome back to Chapter 2, where we're going to talk about atoms, molecules, and ions, periodic table, its development, all that fun stuff. So again, this chapter should be very much review from Chem 1, a little bit of Chem 2 in there, but mostly Chem 1. So we're going to kind of breeze right through this stuff. We'll see if we can get it all done in one video, but I think we're going to pause in the middle of the chapter. So go ahead, remember to pause at the end of each slide so you can write down the notes, or watch the whole video and then go back and pause as you need to write down what you need. Alright, so if we're going back, way back in history, if we're talking about, what is matter? What is the universe made of? When people, say, oh, what's this stuff that I'm holding in my hands? What is it made of? If we go way back, some of the early ideas that, match up to what it ends up really is happening. We go with Democritus, who said that, as you go smaller and smaller and smaller, eventually you're going to get to a smallest possible unit, which he called atomos, meaning uncuttable, indivisible, that must make up all nature. And this idea did not get widespread adoption. You had more people going with the earth, air, fire, water stuff, or, salt, sulfur, mercury, just a few elements as the building blocks of everything. But then in the 1800s, we've got John Dalton, who kind of went back to this idea of there must be something small, there must be something that's a basic building block for everything. And so using a few of his laws that he knew about, and in case I think constant composition he actually came up with, we have constant composition, we have the law of conservation of mass, and we have the law of multiple proportions. And so combining those three laws, he came up with a pretty good idea of what is making up matter. So constant composition, we talked about this in Chapter 1, that every compound has a definite composition, a fixed ratio of the atoms in it. This was Proust, so sorry, that was not Dalton, Proust. And so Dalton used that one. He also used total mass, that total mass at the beginning and the end is the same. Nothing's created, nothing's destroyed. That was, of course, Antoine Lavoisier. And the third one, so here we go. Here's the John Dalton one. That if you have two elements that make more than one compound, the masses that combined will always be a ratio. And so this is one where, say you have a compound of carbon and oxygen. It could be a ratio of, say, if I'm simplifying right, divided by 2, it would be 6 to 8. Oh no, so that would be 3 to 4 for one compound, but then it would also be a ratio of 12 to 32. That's both 3 to 8. So, well, what 3 to 4, 3 to 8? What's that? Well, carbon monoxide, because carbon's 12, oxygen's 16. That's the 3 to 4. But carbon dioxide, well, that's 12 to 32. Well, that's going to be your 3 to 8 ratio. So either way, it's always small whole numbers. That they're always going to go that way. And then once we know formulas, oh, carbon monoxide's 1 to 1. Carbon dioxide's 1 to 2. And so we figured out there that it's got to be these small whole numbers. That's how the ratios work out. All right. So if we keep going on, he then came up with a theory that had 4 postulates, 4 things that he was proposing. The first is that, okay, every element is composed of small things named atoms. So, just, okay, atom's the smallest bit. Democritus, like what you're saying. But then he adds on to it. He didn't say the atoms were identical. In fact, he said all atoms for a specific element are identical to one another. But when you have different elements, they have different atoms. So iron, the element, is made of iron atoms. And that's different from copper atoms. And those are different from nickel atoms or any other metal or any other element. The atoms are different. Now, this postulate is not correct. Dalton did not know about isotopes. We'll get to them later in this chapter. But for what he knew about, this one worked pretty well. And as far as atoms of one element being different from atoms of the others, that part's good. Postulate number 3. Atoms of an element are not changed by chemical reactions. They can't be created or destroyed. So here's using Lavoisier that no, oxygen, as he shows here in the picture, oxygen never becomes nitrogen. Oxygen always stays oxygen. Carbon always stays carbon. These things can't change between each other. All right? And then number 4, atoms of more than one element combine to form compounds, and the compound is always the same number and kinds of atoms. So water is always H2O. It must always be H2O. If you make it H2O2, it's not water anymore. It's hydrogen peroxide, different chemical. So all water is H2O. All carbon dioxide is CO2. These things must be the same. So you can see there that, if you go through there, his postulates are pretty good. There's some where, with extra knowledge that we have, we can say, oh, this one's wrong because he just didn't have enough information. But for what he knew, these things are all very, very good. And so then we'll move on to, well, what about this extra information he didn't have? So we got some discoveries that are going to, tell us more about atoms. We had to discover about electrons using cathode rays. We had to figure out what radioactivity was and where it's coming from. And then we had to know about what's the nucleus, what's the protons, what are neutrons, where did we find out this stuff from? All right, so if we go through there, let's start at the beginning. We got electrons, which were discovered in cathode rays, where it's just an empty tube. Notice the nuclear sign there. You hook it up to some electricity, and if you turn the electricity on, you have a glowing beam that travels from one side to the other, from the cathode to the anode. But the beam, this light beam, it's charged, because if you hold a magnet up to it, that light bends. You can see that green light trailing off to the top there, attracted to the magnet. Or if you use the other end of the magnet, they'll be repelled. And so J.J. Thomson figured these things out in 1897. So here we have a kind of more schematic. And so what he was able to do is say, well, wait a minute, if a magnet bends it, I can figure out the strength of a magnet if I actually use electrically charged plates, so I can kind of tune it to say, oh, if it's this strength, it'll be this much that it's bent. And by doing that, he figured out a charge to mass ratio. So he didn't know the charge of these electrons. He didn't even know it was an electron. He did not know the mass, but he knew that the ratio between them was that it's got to be 1.76 times 10 to the 8th coulombs per gram of whatever this mystery substance is. Right? So if you knew one, you could figure out the other. And that's what it says here. Once you know the one, you could determine the other. So then it's just, well, how do we figure out the charge, or how do we figure out the mass? Well, we have Robert Millikan figuring out the charge by using what was called the oil drop experiment. So he's got oil drops that, think about like a perfume mister where he just has tiny, tiny oil drops. And some of them will fall through a hole in this plate. And these plates, top and bottom, again, electrically charged. And if it's a very large plate, a very large drop, they'll fall near the bottom. But if they're light, they'll stay up top. And the reason for that, well, we have X-rays. And these X-rays are causing electrons to be deposited on these oil drops. So they pick up charge. And so the heavy ones fall to the bottom. The light ones get magnetically pushed to the tops. But certain ones will be just the right size and have just the right number of electrons that they will float in the middle. And then he had a microscope here looking at that middle. So he could say, oh, well, with my microscope, I can figure out how big the drop is. And I know the density of this oil. So if I can measure the radius of these drops, their spheres, use geometry, okay, I know how big that is. I know the density. Now I know how massive it is. And if I know how massive it is, I know what the charge is. So you put all this together. If you put all this together, you can figure out what is the charge of a single electron, and it's around 10 to the negative 19th coulombs. They are tiny. All right. Now, what about some of the other particles? Well, we have radioactivity. This is the spontaneous emission of high-energy radiation, whether it's particles or energy. First observed by Henri Becquerel, also studied by Marie and Pierre Curie. All three of them won a Nobel Prize together for it. And so we see that, okay, these atoms, it's not just that there's electrons in there. There must be some other subatomic particles. These things have energy associated with them. How can we put this all together? Well, first let's talk about the three types. So if we have something that's radioactive and we send it through a filter so that everything's going in a straight line, and we pass that again through these electrically charged plates to induce a magnetic field, what they found was the alpha particles were deflected a little bit. And they went towards the negative plate, so they must be positively charged. Okay? We have some other particles that are deflected much, much more. And they go towards the positive plate, they must be negatively charged, so they call them beta particles. These are actually electrons, and since electrons are lighter, they get deflected more. If you take AP Physics, you'll learn all about this. Hopefully. I can't remember where electricity and magnetism go in with AP Physics, but hopefully, take a good college physics course, you'll learn about why this happens. Gamma rays, they don't get deflected because they're not charged, so they just go in a nice straight line. But these are the three types of radiation that Becquerel and the Curies figured out, and so there's their Nobel Prize for it. And so if we put this information together, we go back to J.J. Thomson, the guy who did the cathode ray tubes. He came up with the plum pudding model where we've got this sphere of positive charge that makes up most of the atom, but then we've got these teensy tiny electrons floating around that are the negative charge that cancels it out. And it's those tiny particles that get ejected from the cathode ray when you zap them with electricity. And so it's called plum pudding because, well, he was British. I like to think of it as rice pudding, where you imagine like if you had ginger and nutmeg as spices, those little tiny flecks of spice that are in there, or raisins, like I put raisins in mine, they're spread out. But either way, they're just kind of floating around. But this is a theory. It's a model. Well, let's figure out, we have to test theories to make sure that they hold up to scrutiny of the data. And so Ernest Rutherford, he was doing that. He believed in plum pudding, but he wanted to double check it. So he shot these radioactive alpha particles, that's what the A is there, that's an alpha, shot them at a very, very thin sheet of gold. This gold was just a couple atoms thick. And so he was expecting, if plum pudding is correct, that all of these particles should go straight through. And if there was any deviation, okay, maybe the gold foil wasn't perfectly thin in the spot, maybe it needs to be better. And sure enough, 99.9 odd % go straight through. But some of them do get deflected a little bit. And more worryingly, some of them get deflected almost completely. Some go backwards. And so it's like, well, wait a second. If some are going backwards, that can't be right. I must have messed up the gold. Do the experiment over and over. This same pattern holds every time. That most go straight through, but there's always some that are deflected in all other directions. How can we explain this? Well, if they're deflected that much, and it's not just that the gold's messed up, that you repeat it, there must be something different going on. Plum pudding cannot be right. There must be something with a lot of mass in the atom that if the particle happens to hit that spot, it's deflected. But that mass must be very, very tiny, or as far as volume-wise, where that would explain why so many of the particles go straight through and don't get deflected at all. So how do we, put these two together? Well, that's where we get the idea of this nucleus. Very, very small, very dense positive center, and then the electrons are taking up the rest of the space. So the idea here is if you have an atom that's about 1 angstrom, an angstrom is 10 to the minus 8th centimeters, or 10 to the minus 10th meters. That's that A with the circle on top, an angstrom. The nucleus would be about 10 to the minus 4th angstrom, so incredibly tiny for an atom that's about 1. To put that on a scale you might understand better, a basketball is about 1 foot wide. So if the nucleus was the size of a basketball, then the electrons would take up a space here that was about 2 miles wide. That's the scale we're talking about. We also have to discover these other particles. So he just said the positive charge was in the middle, so protons were discovered later, or kind of reasoned out to say, okay, well, this has got to be where our positive charge is. Neutrons, we'll find out on another slide how we figured them out. But if we sum up these three particles, and again, this is all review from Chem 1, protons have a positive 1 charge, relatively speaking. Neutrons are neutral, electrons are negative 1. Again, this is that 10 to the negative 19th charge that we talked about for the charge and electron. Just we have a relative scale, plus 1, minus 1. We also came up with a relative scale for mass. These things are extremely tiny, but we came up with the atomic mass unit scale. And so protons and neutrons in Chem 1, we just said they were 1. Really, there is a slight difference here, 1.0073 versus 1.0087, but we usually round it to 1, no big deal. And electrons, well, that's 5 times 10 to the negative 4th, so that would be 0.0005. Well, that's very tiny. That's why it always gets rounded down to 0. It's so small that we really don't care about it. as it doesn't affect the mass in many ways. Oops. All right. So how do we know which element an atom is? Well, we talk about its atomic number, which is the number of protons. And since atoms don't have an overall charge, in a neutral atom, the number of protons will always be equal to the number of electrons. If we want to describe this with a symbol, we write the symbol of the element. We'll put the mass number, which is protons and neutrons, up in the corner there. We'll put the atomic number, which is just the number of protons, down there in the bottom left. A lot of times, remember, that can get left out because if we have the periodic table, if we look up carbon, we see that it's always atomic number 6. So there's no real need to keep that there. But if we want to be complete, we would put that. All right. Notice that these all come before the mass number up top, atomic number at the bottom, and then symbol goes there. All right. Isotopes. So this is one of the places where Dalton was incorrect. He said all atoms of the same element were identical. Turns out not really. They're close, but not exact. They're all identical in the number of protons, but they are different in the number of neutrons. So remember, iso means something the same, and so isotopes are the same protons. So for instance, here are 4 isotopes of carbon, and you can again see here's the symbol with the C, and then the mass number is in the top left, and like we just described, the atomic number was left out of these. All of them have 6 protons, all of them have 6 electrons when they're neutral, but the neutrons is different. Carbon 11 only has 5, carbon 12 has 6, carbon 13 has 7, and carbon 14 has 8. As it says here, carbon 12 is 99% of the carbon in nature. So you can understand if it's the 1800s and they're looking at a sample of carbon, if 99% of it is all one thing, well, you're going to think that all of it's one thing. All right. That's atomic mass unit. When we said, okay, protons and neutrons are about 1 atomic mass unit, well, that's where we can see, well, that's because the heaviest atoms, the very heaviest at the bottom right of the table, they're still 4 times 10 to the negative 22nd grams. Just some incredibly small number. And so if we look at that and say, well, what is that the other way around? Well, that means 1 atomic mass unit is about 1.66 times 10 to the negative 24th grams. You can kind of see, okay, wow, if 1 proton is that much, well, now we can see where it's going from there for why it would be so much more. And if you want to have fun for a second, pause the video, take that number, multiply it by Avogadro's number, and see what you get. Okay, atomic weight. Now here's the thing, in the real world, we're not using a single atom. We're not using just a couple of them. We're using large amounts. We're not using 10 to the 22nd. We're using grams that we can measure on the scale. So it turns out that those isotopes, they get, it's a pretty even distribution. I know in AP Stat, they talk about you need to have a good number of samples to make sure that your overall sample is good. And depending on who you talk to, it might be 20, it might be 25. But if you have a decent sample size, you can be relatively certain that, it's representative. Well, we're not talking about 25 atoms or molecules here. We're talking about 10 to the 23rd usually. So we can be definitely sure that our sample is representative. And so we want to talk about atomic weight, which is we say, well, what about the average weight of all the isotopes for how much they are? And so to calculate the atomic weight, the atomic weight, which is the number you see below the element symbol on the periodic table, you take the sum, there's your sigma notation from calculus, that's the sum, so add up all the atomic masses times what their percent abundance is. So fractional natural abundance or percent abundance for all isotopes. This is the exact same way that we calculate your grades in school. We say, okay, take your grade on all the summative assignments and then multiply it by, say, the 70% that summative is worth. And then take your grades for the formative and then times it by the 30% and then add those two numbers together. So for carbon, with those 4 isotopes, you would have 4 numbers. The mass of carbon 11 times its percent. The mass of 12 times its, and so on. And then you'd add those 4 numbers together to get the mass of carbon. And so what we tried to do when we figure out, well, what is an atomic mass unit? How did we get this definition? Well, what we said was, let's take a pure sample of carbon 12 And let's say it is exactly 12. And then everything else would be based off of that. So even though the protons are really 1.0073, this is how you sometimes get numbers that are slightly above the whole number or slightly below the whole number, because we're saying carbon 12 is exactly 12. Everything else is relative to that. All right. And then this will be our last slide for this section of the video, or this particular video. How did we get these? How do we know about these? How do we even find out about isotopes and neutrons? Well, it was using something called a mass spectrometer, which is a basic one. It's set up here, that you have a sample that you shoot into a tube and you go ahead and ionize it. You give it a charge, and then you have some magnets that can be varied in strength. And so we said the things that are lighter will bend more. The things that are heavier will bend less. And so you make sure that there's a bend in your path, and then you vary the strength of the magnet to say, okay, what weight should have the proper bend to make this work? So we go through, and in this case, the chlorine-35 would get through and be detected, and there it would go. But then the 37 is being split off to the side. It's not being detected. But as we vary the magnet, so as we kind of scan from left to right, we'd say, okay, 34 would be scanned, but there's nothing there. There is no chlorine-34. Oh, but then we get to chlorine-35, and now we see it. And then we get to 36. The magnet got stronger. Oh, but we don't see anything because there is no chlorine-36. Oh, but then we make it a little more, and yes, we see chlorine-37. And so when people saw these multiple spikes, when they're only expecting to see one thing, this is what led them to understand, hey, there must be some other part of the atom that's giving it mass, but it's not affecting the charge. So you can see there, so based on how big these peaks are, you can say how much of each element are there. So in this case, about 75% of chlorine is chlorine-35, about 25% of it is chlorine-37. And so when we average those two numbers, that's why when you look on the periodic table, chlorine's atomic weight is much closer to 35 because there's more of it. All right, yeah. And we're going to stop there for this part of the video. In part 2, we'll talk about the periodic table, how we use these parts of the atom to arrange the periodic table, how we can get the trends and all that. So still review, but make sure you come back and write down those notes as well.